Hello class, I hope you're having a wonderful day. Today I would like to talk about a velocity time graph. We're going to look at a T-chart or a table, and then we're going to generate a velocity time graph, and then we're going to calculate the area under the curve so we can calculate the displacement, and we're also going to talk about the acceleration of an object today. So let's go ahead and get started with our problem. Our problem says the velocity of a car changes over an 8-second time period as shown in the table below. And so what the practice problem is referring to is the table that the problem provides for us. We have a T-chart. So in the left-hand column we have the time in units of seconds, and this is our x value. So this is our independent variable, and we have in the right-hand column velocity in units of meters per second, and this is our dependent variable. So this is the y value. And so what we have is 9 ordered pairs, and I've already started drawing the velocity time graph. So like I mentioned earlier, on the left-hand side of our column we have the x value. So time is our independent variable, and velocity is our dependent variable. So as you can see, at a time of 0, we start at a velocity of 0 meters per second, and then at 1 second, we're at a velocity of 2.5 meters per second. At 2 seconds, we're at a velocity of 5, and so as you can see, our velocity is changing. So for the first several seconds here, we do not have a constant velocity, okay? So let's go ahead and plot all of our ordered pairs here. Okay, so we have something that looks like that, okay? So in part A, all we're doing is creating our velocity time graph, which we've taken care of. In part B, it wants us to calculate the change of the car's displacement during the first 2 seconds. So what we're going to do is take a look at our velocity time graph. And on a velocity time graph, we know that the area under the curve represents the change in displacement of the object. So in part A, it's wanting to know the first 2 seconds. Okay, so we've got right here, and if I identified my ordered pair here, I have 2 seconds and 5 meters per second. Okay, we know that this is a right triangle here, and so what I'm going to do is add a quick note here. The area under the curve on a velocity time graph represents the object's displacement. Okay, so what we're going to do here is calculate the area under the curve. So since this is a right triangle, we know the area equals 1/2 base times height. So 1/2 times my base, and if you notice, so we have time on the x-axis, our base represents our time interval, delta t. Okay, so delta t here, and our height represents our velocity. Okay, so I have 1/2 times the time interval. We have 2 seconds minus 0 seconds. So I have 2 seconds times our final velocity at 2 seconds, so 5 meters per second. So what we have is 5 meters per second times 2 seconds is going to be 2 meters, because our units of seconds cancel out. So 10 meters divided by 2 is equal to 5 meters. So on part B, our answer is 5 meters, the change in displacement from 0 to 2 seconds. Okay? Now, in part C, it's wanting to know what the change in the car's displacement is from 0 to 4 seconds. So right here, let's locate 4 seconds on the x-axis. Right here. And if I identified this ordered pair, I have 10 seconds, 4 seconds, 10 meters per second. And once again, we're going to calculate the area under the curve. We have a right triangle, so we're going to use the same equation. Area is equal to 1/2 base times height. So what we've got here is 1/2. My base is 4 seconds, so 4 seconds minus 0 seconds. 4 seconds times a height. So my velocity at 4 seconds is 10 meters per second. So 10 meters per second times 4 seconds is going to be 40 meters. Our units of seconds cancel out. So 40 meters divided by 2, so our change in displacement is 20 meters. Okay? And so one concept that I really want to point out is the difference between part B and part C. So in part B, the question is wanting to know the change in displacement during the first 2 seconds. You guys calculated that to be 5 meters. So, I want to ask the question, would it be safe to assume that if we just double our time, so if you notice we're going from 0 to 2 seconds to 0 to 4 seconds in part C. If I double the amount of time, is it safe to assume that we're just going to double the change in displacement? Well, the answer is no. We cannot assume that, because if you look at this graph, we have a changing velocity, okay? And we know that the slope of the line on a velocity time graph represents the object's acceleration, okay? So, since we have an acceleration and a positive acceleration, since the slope of the line is positive, we cannot assume that if we're just going to double our time period, that we're going to double the displacement. So we cannot do that. We have to calculate the area under the curve. Okay, in part D, it wants us to calculate the total displacement of the car for our time interval, which is 8 seconds. Okay, so what I'm going to do here is I'm going to first split this up into 2 areas. We know this is area 1. We'll call this area 2. And so for the total displacement, so delta D subtotal, this is going to be the sum of our areas. And I'm going to use the capital Greek letter sigma here. This represents the sum of. So the sum of the areas. We have 2 areas that we've split our graph into. So this is going to be area 1 plus area 2. So for area 1, our base equation is going to be 1/2 base times height. And for area 2, our base equation, we have a rectangle here, so let's say base times height. So for area 1, 1/2 times my base. So this is my time interval, 5 seconds minus 0 seconds. So 5 seconds. We're going to multiply by the height. This is 12.5 meters per second. For area 2, we have base times height. So base, this is our time interval. We have 8 seconds minus 5 seconds, so that's 3 seconds. For our height, we have have 12.5 meters per second. And so once again, change in displacement, our total change in displacement is area 1 plus area 2. We're going to add these values together, so go ahead and take out your calculator. Let's calculate this. I have 12.5 meters per second times 5 seconds. We're going to divide that by 2. This is going to give me 31.25 meters plus I have 3 seconds times 12.5 meters per second. This is 37.5 meters. And so this looks like this is going to be 68.75 meters. Okay? All right, so in part E, it wants to know what the slope of the line is from a time interval of 0 to 4 seconds, and it also asks, what does the slope of the line represent? Okay, so let me erase this here. Okay, so what we're looking at is the slope of the line from 0 seconds, so my ordered pair here is 0 seconds, 0 meters per second, to 4 seconds. So I have 4 seconds, 10 meters per second. Okay, we know that the slope of the line, our equation, is y2 minus y1 divided by x2 minus x1. Well, to be a little bit more specific, let's change our variable here. We know our y value is velocity, so what we have is final velocity minus y1. This is going to be our initial velocity divided by x2. Well, our x value is time, so this is going to be time final minus x1 minus time initial. So our final velocity is 10 meters per second minus initial velocity of 0 meters per second divided by time final. We're looking at 4 seconds minus time initial, 0 seconds. So 10 meters per second divided by 4 seconds is going to be 2.5. So our numerical value is 2.5, but let's take a look at the unit value here. So in my numerator, I have meters per second. I'm dividing by units of seconds, and algebraically we can say that this is seconds over 1. And whenever we divide fractions, it's like multiplying by the inverse of the denominator. So I have meters per second times the inverse of our denominator. This is going to be 1 over seconds. So when we multiply fractions, we just multiply straight across. So I have meters per second squared. So my answer here is 2.5 meters per second squared. And the second half of part E, it asks, what does this represent? Well, the slope of the line represents the acceleration of the object. So our answer is 2.5 meters per second squared, and this is the acceleration of the car. And this is from a time interval of 0 to 4 seconds, so the average acceleration of the car. In part F, it wants us to calculate the slope of the line from a time of 5 seconds to 8 seconds. And then what does this represent with respect to the car's velocity? So up here, if I identified this ordered pair here, I would have 5 seconds, 12.5 meters per second. Over here, my ordered pair is 8 seconds, and the velocity is still 12.5 meters per second. So looking right here, if we calculated the slope of the line, we have a horizontal line. And really, if you take a look at our T-chart that the problem provided for us, at 5 seconds, the velocity of the car is 12.5 meters per second. 6, still 12.5 meters per second. And so on to 8 seconds, we have a velocity of 12.5 meters per second. So we have a slope from 5 to 8 seconds of 0. And our units are meters per second squared. So right here, the slope is 0 meters per second squared. And this means the acceleration of the car is 0 meters per second squared. But the problem is specifically referring to velocity. So how are we going to describe the car's velocity? Well, if we have an acceleration of 0, our velocity is not changing. That means we have a constant velocity of 12.5 meters per second. So let's just simply say the car's velocity is constant at 12.5 meters per second. And this is from a time of 5 seconds to a time of 8 seconds. So I hope that us working this together has really helped you out on one of the velocity time questions that we covered. So if you have any questions, please contact me by phone or send me a message over Canvas or send me an email, and I will be more than happy to help you. I hope you have a wonderful day.